Hi everyone, welcome to this presentation entitled Optimum Design of Power Inductors. This is the outline of this presentation. First we will see an introduction, then we will see how to calculate the core losses and the winding losses of a power inductor. We will talk about the conventional optimum design, and later we will present a correction to the conventional optimum design. Finally, we will show an example. This video is a continuation of this previous video, Power Electronics number 4, entitled Quick Design of Power Inductors. So if you are not familiar with the design of power inductors, it's very advisable that you first take a look at this previous video. The motivation of this video today comes from the previous video, Power Electronics number 4, Quick Design of Power Inductors. We presented in this previous video a methodology to design power inductors. Here I am showing one of the slides of these previous videos of this methodology. And at step number 10, we said that we have to compare core and winding losses, and that a good design should verify that the core losses and the winding losses should be approximately equal. So after publishing this video, I got several questions and comments asking about what is the reason why these two powers should be equal. So I decided to upload this video today to clarify this point in the design. Now we are going to calculate first the core losses. We have here our inductor. As usual, we have the core with the different parameters that we already know. We have a current circulating through the winding. In a general situation, the current has a DC component, IDC, and an AC component. We have here I hat, which is the peak of the AC component of the current. And then once we have selected the core material and size of the core, then we have only two parameters to play with. One is the number of turns of the winding, and the other is the length of the air gap G. So we know also these two equations. Number one is the inductance, which is equal to the number of turns squared divided by the reluctance. We know that the reluctance is given by this expression, is a geometrical parameter of the core, and then we can calculate the magnetic flux using this expression here. The AC component of the magnetic flux is equal to the magnetomotive force, which is the number of turns times the current divided by the reluctance. So using these two expressions, 1 and 2, then we can calculate the magnetic flux in this way, and from it we can calculate the magnetic flux density B. So this is the peak of the magnetic flux density using this expression here. Now we can do several designs, but in all of them we want to have the same value of the inductance, of course, so we can consider the inductance L constant. So then the peak of the magnetic flux density can be expressed as a constant, K1 divided by the number of turns N. And K1 has this value here. We also know that the losses in the core of a magnetic material can be expressed by using this equation here. Depending on the operating frequency, rise to this parameter alpha, and depending on the magnetic flux density, the peak of the magnetic flux density, rise to another parameter beta. We have another constant here, K2, and times the volume of the magnetic material. Now, if we consider that we are operating at constant frequency, Then this part here will be a constant, the volume is another constant, and also the typical value, especially for soft magnetic materials like ferrites, is beta around 2. So then we can express the core losses as shown here. And finally, we can obtain this expression by substituting this expression here for the magnetic flux density here in this other equation. Then we get that the core losses are equal to a constant Kc divided by the number of turns squared, and this is the value of the constant Kc, K1 squared times K3 times the effective volume of the core. Now for the winding losses, we can calculate these losses using this equation here is equal to the resistance of the winding times the RMS current squared. And the winding resistance can be calculated using this equation is the resistivity of the copper times the winding length and divided by the total area of the copper. The winding length can be obtained as shown here is the number of turns times the average length of a turn. And this is a parameter that can be obtained from the information of the coil former. Here we have L sub m for this type of former. And then the copper surface can be obtained by multiplying the number of strands times the area of each strand. So as shown here, the winding is made by many different strands, and this is the total surface of the copper in the winding that can be calculated as shown here. And of course, the area of this strand is obtained with this other expression. The S is the diameter of each strand. Now, as we have seen in the design process, the total winding area AW is equal to the number of turns times the surface of each turn, and we do the design so that the total winding area is going to be equal to the packing factor times the available area AN. The available area AN can be obtained also from the coil former information, and the value of the packing factor, of course, is between 0 and 1. Usually a typical value is 0.3. So from this equation here we can obtain the number of strands as shown here is the packing factor times the coil former area divided by the number of turns times the area of each strand. And then we can take this value and substitute this value here in equation 2, and then take all this, which is the winding resistance, in equation 1. And then we will see that the winding losses are equal to a constant Kw times the number of turns squared. And this is the value of the constant Kw. So now we have everything. We have the core losses, which are reversely proportional to the number of turns squared. We have the winding losses, which are proportional to the number of turns squared. And then we have the total losses, which are the addition of the core losses and the winding losses. And then we have this expression here. So the optimum design is the design that minimizes losses. So in order to minimize losses, we calculate the derivative of the total losses with respect to the number of turns and equal this derivative to 0, as we know. So we obtain this derivative and equaling it to 0, and then solving for the number of terms, we get this value. For the optimum number of terms is Kc over Kw raised to 1 over 4. Once we know the optimum value of the number of terms, then we can calculate the optimum value of the reluctance, and from it, using the equation that we have seen before, we can obtain the value of the air gap length. Now, if we calculate the value of the core losses and the winding losses for this optimum design, by substituting this value of the number of terms in these expressions here, we will see that they are both equal and equal to this value, the square root of kc times kw. And then, of course, the value of the total losses for the optimum design will be equal to twice this value, twice the square root of kc times kw. If we represent this graphically, we represent here the power as a function of the number of terms. Then we can see that here we have the core losses. This other curve here is for the winding losses. And then in blue we have the total losses, the addition of both of them. So we can see that here we have the minimum value, the optimum design, when both losses, core losses and winding losses are equal, and they correspond to this value of the number of terms that we have calculated here. So this is the reason, as we have seen in the previous video, that in the conventional design we try to make the design so that the core losses and the winding losses are close to each other, because in this way the total losses are going to be minimum. Now we are going to do an example of optimum design. For this, the first thing that we need is the characteristic of core losses of our magnetic material. We are going to take as an example this material N87. We have here some information of the core losses at different magnetic flux densities and different operating frequencies. Note that these values here are measured per unit volume. So what we have here is the power loss density in the core. We have this other representation. Here we have the power density as a function of the magnetic flux density and operating at 100 kHz and two different temperatures. We are going to take in this example the 100 degrees operating temperature. So it corresponds to this line here. We can see that this is a straight line. So we know that the expression for the power loss density is like this. It's a constant times the frequency raised to an exponent times the flux density raised to another exponent. Now we are operating at fixed frequency, so all this is a constant that we are going to call K3, as we have seen before. And if we take logarithms in this expression, then we can obtain this other equation here, which in double logarithm representation corresponds to a straight line, as we can see here. So we only have to take 2 points. We are going to take this point here on Y, which corresponds to this point here, 375 kilowatt per cubic meter. And then we take this other point here, X, and then we have these 2 points, Y and X. And by substituting in this expression, we obtain these two equations that they are very easy to solve, and we get this value for K3 and this other value for the exponent beta. So this is the final expression. So one thing that we can see here is that the value of beta is close to 2, but is not exactly 2. Here for this material we have 2.758. So we might wonder here if our analysis, our previous analysis, would be accurate enough. So now we can do a correction for more accuracy in our conventional design. If we go back in our reasoning, then we can say that the core losses can be expressed like shown here, in which we are keeping in a general way the exponent beta. Instead of using 2 here, we are using a general value beta. So we can say that the core losses are going to follow this expression here. For the winding losses, we keep the same expression with this value for the constant, and then we have that the total losses are as shown here, and this is the new expression considering a general value of the exponent beta. Again, we can do the same. We find the minimum total losses by taking the derivative and equaling it to 0. We get this expression here, and then this will be the value of the optimum number of terms if we keep a general value of beta. So we can see that if beta is equal to 2, then we have the same expression as before. And again, once we have this optimum value for the number of terms, then we can calculate the total losses, the losses in the core, the losses in the winding, and then from the number of terms we can calculate the reluctance, and finally the air gap length, as we have seen before. Here we can see the implementation in WinPython of an example. Here we have the different parameters of our material. We want to implement an inductance of 75 microhenry that is going to handle a DC current of 2 ampere and AC current of 1 ampere. This is the code that we have selected with these different geometric parameters. The operating frequency is 100 kHz. This is the diameter of the wire and the packing factor. So here we have the expressions that we have seen in this presentation. We have K1, Kc, Kw, and then with this expression here we calculate the optimum value of the number of turns. Here we calculate the AC component of the magnetic flux density, the DC component of the magnetic flux density, the peak flux density, the air gap length, and then the core losses, the winding losses, the total losses, the number of strands that we have to use to implement our wire in the winding, and then the total length of the winding, the area of the wire, the total copper area, and the resistance of the winding. And with this we have everything. We only need to plot the results. So here we can see the script in WinPython. This is the same that we have seen right now, and this is the printing of all the results. So we can run this script, and then we can see here the results. We get an optimum number of turns of 20.6, the air gap length around 0.2 millimeter, the AC flux density, the DC flux density, the peak flux density. We have to check that this value is lower than the saturation value of the material, which is 0.4 in this case, so this is okay. Here we have the number of strands that we need to implement our winding, the winding length, the winding resistance, the winding RMS current, and then we have the winding losses, 0.17 watts, and the core losses, 0.12 watts, and the total losses, which are around 0.3 watts. So we can see that these two losses, the winding losses and the core losses, are very similar but are not exactly the same, because we are considering the true value of the beta exponent, and not considering the value of beta approximately equal to 2. So this is a more accurate design than the conventional design, in which what we do is to have equal winding and core losses. Now we can do the plotting of the curves. For this we have here this other cell in which we are representing the different functions corresponding to the core losses, the winding losses, and the total losses, and doing the plotting of these functions. So we can run this cell again, and then we can see here in the plots area, we can see the representation. So we see the core losses in red, the winding losses in blue, and the total losses in green. So because we are considering the true value of beta, which is something like 2.7, we can see that the minimum is around this point here, which is not exactly in the cross point of both curves, PC and PW, but in any case it's very close to it. So in many cases we can consider for a quick design that the optimum point will be when both core losses and winding losses are equal. Now we can do a quick simulation to check our design in LTspice. So here we have our model of our inductor. This is the reluctance of the core. Here we have the air gap, and here we have the winding. Then we have here a resistance and a voltage source, and we have adjusted the voltage source in order to have the value of the current that we have in our example. The operating frequency is 100 kHz. And then we have here these statements to calculate the different values, and finally the value of the inductance. If you are not familiar with these components are from our magnetics library, which is presented in this video here, Power Electronics number 5, Spice Modeling of Magnetic Devices. So if you want to have more information about this modeling, please take a look at this video, Power Electronics number 5. And now we can run the simulation. We can check first the current through the inductor. So we can see that has an average value of 2 amperes with a peak value of around 3 amperes. And then we can add another pane and measure, for example, the magnetic flux density. So we have an average value, a DC value of 0.23 Tesla, which is similar to the value that we have calculated. And also we can measure the peak-to-peak value. And the peak value, here the peak-to-peak value is something like 0.26 Tesla, which is also very similar to the value that we have calculated theoretically. And now we can press Ctrl L to see the result of the inductance. So here we can see the different values that we have calculated, and here on this line we can find the value of the inductance, which is very close to 75 microhenries as expected. Finally, we can consider what happens if in our application, if in our converter, the operating frequency is variable. Here we are highlighting in blue the parameters that are going to change with the operating frequency. When we calculated the core losses, we have parameter K3, which is equal to this value here, and therefore is dependent on the frequency. And also this parameter beta is dependent on the frequency. So finally we can say that the core losses curve is going to change with frequency. Regarding the winding losses, in principle, we are not considering any effect of the frequency. In our analysis, we have neglected the effect of the frequency in the winding resistance, we are neglecting the skin effect and the proximity effect, so we have the same curve at all frequencies. So what we have is that the total losses are like this. We have a change here depending on the frequency on the core losses, and therefore we can do the same to calculate the optimum value of the number of turns, and we find that the optimum number of turns is going to be different at each operating frequency. We can see this also graphically. What is happening is that the curve corresponding to the core losses is going to change in frequency. If we increase the frequency, the losses are going to increase, while the curve corresponding to the winding losses keeps almost the same. So the optimum operating point is going to be around the cross point of both curves, the core losses and the winding losses, as we know. So if this is the nominal operating frequency, FO, then the optimum of the design will be for this value of the number of turns. But if we increase the frequency or we decrease the frequency, then the optimum number of turns is going to be different. And this is why it is not possible to optimize the operation of the magnetic components in power converters that operate at a variable frequency. So this is one of the reasons why it is so important to keep the operating frequency of the converter constant in some critical applications. Well, this concludes this presentation today. I hope that this video has been interesting for you. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.